There are walls in Peru that flex like rope during earthquakes, while concrete shatters like glass around them. University of Tokyo researchers recorded the phenomenon in 2001. Stones weighing 100 tons each, moving as one organism during seismic events. No cement, no grout, no chemical bonding agents. Friction and precision geometry doing what $50 billion in seismic engineering cannot replicate. We didn't stop building with dry stack stone because it failed. We stopped because a wall that needs no cement threatens a $400 billion concrete industry. A structure that lasts 2,000 years without maintenance cannot generate recurring revenue, and what cannot be sold cannot be controlled. This is the story of dry stack stone masonry, the building method that outlasted every empire that used it, and the industry that buried it under building codes written in concrete. The Sacred Valley of Peru stands as one of the most seismically active regions on Earth. 600 years ago, Inca engineers faced an impossible challenge, building structures that could withstand the violent shaking of the Andes Mountains, where two tectonic plates collide with devastating force. Earthquakes measuring 7.0 or greater strike every few decades, yet Inca structures remain standing after centuries. Take Sacsayhuaman Fortress, constructed around 1438 AD. Its massive walls feature stones weighing up to 200 tons each, cut and fitted without a single drop of mortar. The joints between these megalithic blocks are so precise that even today, a knife blade cannot be inserted between them. What's more remarkable is that this engineering marvel was completed in just 60 years using only bronze tools. The secret lies in the ingenious principle behind their construction. Each stone was shaped with interlocking surfaces, custom fitted to its neighbors. The sheer weight of the blocks, combined with the friction between their precisely cut faces, creates a structural integrity that modern engineers struggle to replicate. But the true genius is in the flexibility. These walls actually move during earthquakes, absorbing energy instead of fighting against it. This wasn't unique to Peru. Around the world, ancient civilizations independently discovered similar techniques. The platforms supporting Easter Island's Moai statues, built between 1250 and 1500 AD, use the same principles. In Mycenaean Greece, Cyclopean walls dating back to 1600 BC stand firm after millennia. The Great Enclosure of Zimbabwe, constructed between 1200 and 1450 AD, and Japanese castle foundations from the 15th and 16th centuries all relied on dry stack techniques to create earthquake-resistant structures. For over 3,000 years, this was the pinnacle of earthquake engineering. And then we forgot. The rediscovery began in 1950 when the Great Cusco earthquake struck southern Peru with a magnitude of 8.0. Modern concrete buildings throughout the city crumbled. Colonial Spanish structures suffered severe damage. But the ancient Inca dry stack walls, they remained completely intact. Dr. Hidefumi Yamazaki, a structural engineer from the University of Tokyo, became fascinated by this phenomenon. Between 1995 and 2001, he traveled to Peru to study these ancient construction methods. His opportunity came during the 2001 Arequipa earthquake, a massive 8.4 magnitude event. Dr. Yamazaki documented something extraordinary. The dry stack walls moved as unified, flexible systems. Individual stones shifted up to 6 inches during the intense shaking, but remarkably, the walls returned to their original positions afterward, showing no structural damage whatsoever. It was as if the walls were alive, breathing with the Earth's movements rather than fighting against them. Laboratory testing at Tokyo University confirmed what the Inca had known centuries earlier. These dry stack walls demonstrated compressive strength between 2,000 and 4,000 pounds per square inch, comparable to modern materials. But their tensile flexibility was 300% greater than mortared walls. Simulation tests showed they could survive earthquakes exceeding magnitude 9.0. Perhaps most impressive was their longevity, 500 years and counting with zero maintenance. From an economic standpoint, the numbers are even more compelling. Dry stack construction costs between $15 and $25 per square foot, compared to modern seismic concrete at $45 to $80 per square foot. Earthquake retrofitting for existing buildings can run anywhere from $25,000 to $100,000. The ancient solution isn't just better, it's dramatically cheaper. So why aren't we building this way today? The answer lies in a complex web of industrial influence and economic incentives. The Portland Cement Association, founded in 1916, helped transform concrete into a $400 billion annual industry. Today, global concrete production exceeds 4.1 billion tons per year and employs 2.3 million workers worldwide. It's not just a building material, it's an economic powerhouse with tremendous influence over how we construct our world. This influence extends to our building codes. The International Building Code and Uniform Building Code mandate cement-based construction for masonry structures. There are no provisions for dry stack stone masonry, despite its proven track record. Any alternative methods require expensive engineering approvals that most builders simply can't afford. The exclusion is systematic. Engineering schools teach only mortared masonry techniques. Contractors receive training exclusively in cement-based methods. Insurance companies refuse coverage for what they deem unconventional construction. Mortgage lenders reject financing for buildings that don't conform to standard codes. The financial barriers are prohibitive. Structural engineering approval for dry stack construction can cost between $15,000 and $15,000 and $15,000 and $50,000. Seismic testing requirements add another $25,000 to $25,000 to $25,000 to $75,000. Building permit delays can stretch an additional 6 to 18 months, and even if you clear these hurdles, insurance premiums run 40 to 60% higher than rates for standard construction. This isn't a conspiracy, it's economic gravity. A building method that requires no ongoing materials cannot sustain an industry built on recurring sales. Permanence is unprofitable. But how exactly does dry stack masonry work? The technique relies on stones cut with interlocking surfaces and precise angles. Each block is shaped to fit a specific position in the wall. The weight distribution creates compression-based stability, while friction between the surfaces provides lateral resistance. The physics of flexibility is what makes these structures superior during earthquakes. Mortar joints create rigid connection points that transfer stress and become failure points under seismic loads. Dry stack construction, by contrast, allows micro-movements that absorb energy. The entire wall behaves as a single flexible organism during earthquakes, dissipating forces that would shatter rigid structures. The cutting and fitting process is meticulous. Traditional masons created templates using wooden or stone patterns. Each stone underwent progressive fitting and adjustment. Surface preparation employed bronze or steel tools, and final positioning utilized lever systems and ramps. It was labor-intensive but created structures that have outlasted every modern building in seismic zones. The performance specifications speak for themselves. The compressive strength exceeds modern concrete block. The thermal mass provides superior temperature regulation. Natural breathing and drainage manage moisture more effectively than contemporary systems. And the seismic performance surpasses anything we build today, surviving earthquakes above magnitude 9.0. From a materials and cost perspective, the advantages are clear. Local stone costs between $5 and $15 per ton. Cutting tools require an initial investment of $200 to $200 to $200 to $500. Skilled masons command $25 to $25 to $25 to $40 per hour. Yet the total wall cost runs 60 to 70% less than reinforced concrete alternatives. Common misconceptions persist. Many believe walls will collapse without mortar, but properly cut dry stack construction is demonstrably more stable. Tests at MIT have confirmed superior earthquake resistance compared to conventional methods. Despite institutional resistance, a revival is underway. In New Zealand, builders are constructing dry stack retaining walls in earthquake zones. Japan is restoring traditional castles using original methods. California has experimental seismic-resistant projects underway. And in Peru, the maintenance of Inca structures continues using techniques passed down through generations. Recent validation studies continue to confirm what ancient builders knew. Stanford University conducted seismic simulation tests in 2019. ETH Zurich published structural analysis research in 2021. The University of Chile documented earthquake response in 2023. All reached the same conclusion. Dry stack construction outperforms mortared alternatives in seismic events. Legal pathways are slowly emerging. New Zealand's building code now allows dry stack under specific conditions. California has pilot programs for alternative seismic construction. Peru requires traditional methods for national heritage preservation. Japan mandates original techniques for cultural preservation projects. There is a building method that creates earthquake-proof structures by removing the thing engineers say holds them together. It has survived 500 years of Andean earthquakes while concrete crumbles around it. It costs 70% less than modern seismic construction and requires zero maintenance over centuries. The only thing standing between you and walls that flex like living tissue is a building code written by an industry that profits from planned obsolescence. What shocked you most about dry stack masonry's earthquake resistance? Share below and subscribe now. Let's rebuild what knowledge they tried to bury.